Hi, my name is Chris Fitzpatrick. I'm part of Team Gapple, and this is the Lightweight Truck Loading System Presentation 2. For this project, we were presented with a problem. Traditional metal planks for loading bicycles on a truck are heavy, clunky, and challenging to store in the truck. Overall, super cumbersome. And we are looking for a way to offer a lightweight, foldable system, convenient and efficient, so that people can load bikes onto their trucks. And for this project, the primary market is seniors, or also people who struggle with lifting something above their heads or lifting bikes up into the beds of their trucks. And there were 5 main components of this project, 5 main aspects that we wanted to make sure we met this criteria, creating a truck ramp that is lightweight, foldable, easy to handle, inexpensive, and it is oriented towards bicycles and other medium weight wheeled vehicles, something that caps out at 40 pounds but averages out to around 20 pounds. There are a handful of existing products and potential solutions that already exist. And in this case, we have some 1-hinge and 2-hinge foldable truck ramps. These are mainly catered toward motorcycles, ATVs, or other heavier wheeled products. And as you can see, the ideal weight for this is it's over 400 pounds or 400 pounds or 500 pounds for the load capacity. And that is way higher than we would need with our expected extreme of 40 pounds. And also the weight of these ramps themselves is 7.1 kilograms, 15 pounds or 21 pounds. And that's also pretty steep. We're looking for something that's super lightweight, something that can like collapse further and can stow away easily inside of the truck rather than have to leave them at one place or another, or have to come up with additional space in the bed of the truck to fit a ramp. And here are the 3 initial CAD designs. We have a sort of cascading ladder. We have a traditional ramp that has 1 fold and has a bunch of holes in the middle as to reduce the weight. And we also, on the right, have a hinge system, a hinge and plank system. And ultimately, we decided to choose the hinge system. Separate plank and joint design gives more freedoms in plank materials, and it's also customizable. People can easily take out the current planks that are in there if they're worn out, or if they need an alternate size, and they can just replace it very easily. And this we also chose this because it saved research time, and it also will be a lot easier in a mass production perspective to create. It'll save time, it will save resources, and overall be a very efficient way to handle this problem. And of course, we iterated through this design. We had a handful of different versions of this hinge system. We started out with this paper sketch right here, starting out with actually talking about having interlocking wooden pieces and rope and string that crisscrossed. And then we sort of branched off of that, saying, okay, what if we took this idea of this growing size, but we make it into something that's a bit more feasible for what we're trying to do. And we ultimately decided to go with a hinge. And we started out with some pretty interesting designs. These two initially we had this, and then we went to this design, and ultimately decided upon this one right here. And we're still iterating, trying to make sure that it's perfect. But we're pretty dead set on having our final design be at least very similar to what we currently have right here. And here are the actual 3D printed versions of these designs. And if you look closely, you can actually see that there is one component that is missing that's a little bit important. These little axles right here. Yes, we have the two parts of the hinge, but we didn't have an axle, and so that is something that we're going to have to look into purchasing separately rather than fabricating in a 3D printer as well, to ensure that it takes the least amount of effort to open and close and does not buckle or break over time. Here is our tentative final design. As you can see, the ramp can fold into a compact shape, but it can also expand into a long ramp. The joints allow for rotation in one direction only, and it stops it stops at 90 degrees, and then it stops again at 180 degrees, and it cannot condense further and it cannot expand further, as to make sure that it is stable and flat and able to be used successfully as a ramp by customers. The expected length is to be around 7 feet. This is what we've seen in the market for truck ramps. We originally went with a very STEM-minded approach for the size, planning it to be 11 feet as to meet standards of ramp angles and whatnot, trying to make it 15 degrees with the maximum height. But ultimately, we decided that just having a truck ramp that matches what's currently on the market is a much simpler solution than trying to do a bunch of trigonometry for it. And then we developed an iterative design, and it allows for super simple manufacturing and easy addition. Again, people can take out old planks, whether they snap, which we hope it doesn't, or if they want a different sized plank, they can very easily do that, and then reinstall a new one, either of the same size if that works out, or a different size if they prefer that. And some potential changes that we could make are the size, plank design, how we secure the plank into the truck bed, the shape when it's compact, the overall attractiveness of the design, and the ergonomics as well. Here is our joint. As I mentioned before, it can condense down to 90 degrees. It can expand out to 180 degrees. And this was very crucial for the MEs in the group to design, as this is the point at which the ramp faces is going to face the most stress scrutiny, because obviously it's the only moving parts in it. The planks are stable, and if they're secured in properly and have weight applied to them properly, there should be no issues there. And so the joint is where we have to make sure that it doesn't buckle or break. And so we went through a bunch of iteration for this. And so for the fabrication of the joint system, we used an ABS 3D printer filament for the material of the joint system. We will be using the 3D printing machine to fabricate each of the joints. And a total of 12 parts is needed to connect the planks together. And the joints will be connected with a steel bar, just like a little steel rod. And that will be what we have to purchase in order to complete our design entirely. Here is the fabrication of the plank system. Originally, we'll be using PVC plastic sheets. We will be cutting from a 3/4 of an inch by 4 feet by 8 feet sheet, which costs $207.50, and that will be used to create all of the planks for the design. We'll be using a speed jigsaw to cut it. 6 parts will be needed, with each of the different lengths to properly fold the ramp. So it'll go from very small to larger to larger to larger to larger, as to have it so that it can collapse properly and ultimately expand out to 7 feet. And here are the parts that need to be purchased. As I mentioned before, the 304 stainless steel round bar that's going to be used for the hinges, bolts and nuts so that it can properly rest on top of the lip of a truck bed door, and also need a ramp top kit for this as well. Here are the engineering analyses and experiments that we conducted. We had some initial assumptions about how stuff would bend, and also wanted to ensure that what the materials they bow properly, um, and what make sure that it doesn't break, that it maintains its stability, and that it just stays strong, and works under various wear and tear. So here is a finite element analysis with boundary conditions and loading forces to determine the reaction stresses and deflection. So as you can see, the what is it? The ramp will, when it's applied a various amount of stress, it should be able to maintain its strength and be able to withstand the newtons that we expect it to face. Here are the results. The negligible effects due to thermal deformation. 50 Newton shear force applied on the joints, 2 millimeter max deflection along the planks. Difficulty quantifying results due to repeated loading. That's just comes with the tools that we had to conduct these experiments. I'm sorry. And overall, we had no red flags when conducting. And we have some more planned experimentation. We want to transition what we have done virtually in SolidWorks to the real world and test the physical prototypes with distributed loading and a bicycle. Here are the goals that we have met. We have formed our team. We delegated various leadership components of Capstone to each other, which we've been doing a great job of maintaining, leading. We've kindled relationships with our client sponsor and our advisor. And we have come to an understanding of what exactly our client sponsor wants us to develop. And we've drafted out designs, looked deep into things that have already been made, and we've selected design to focus on and flesh out. And we have already began to focus in on that design. We have created prototypes, and we are continuing to remain conscious about what we want to do, changing our design, and just make sure that we create the best products we can with the time and tools that we have. Here are some design challenges that we faced. Obviously, we are developing a lightweight bike ramp for trucks that can be stowed away easily. Retaining the strength while allowing for collapsibility is super important, and we are continuing to test slight variations. At this point, we have focused in on what we really want to create for this Capstone project, and this design has a very good strength to weight ratio, and also has a lot of promise in terms of collapsibility and overall use. And also, so this second challenge we've actually already solved. We have decided to go with the market standard of 7 feet for the ramp, rather than going for the 7.5 feet to 11 feet. And this acceptable angle for truck ramps is mainly sort of oriented toward a factory setting rather than a commercial setting, and we've decided that those standards aren't important enough for us to validate extending the feet of the ramp by a whopping 4 feet. And also, we're looking into the locking and latching system for the product. Obviously, we fold out, and it stays. It doesn't extend further. So those challenges we've overcome for the most part. Here is the final assembly folded out. As you can see, we've got all 6 parts, and they just remain folded out. And we have a bunch of other specs, and we show the decreasing size of the planks as you go further up the ramp. Here is the final assembly folded in. As you can see, it folds up into a nice little rectangular prism, and it's very compact, which is exactly what we're looking for. And here is the joints, and let's see. Obviously, we have the joints designed in a way where they can just be mirrored rather than having to have two separate joint designs, which allows for a lot easier manufacturing and will make it a lot less difficult than having to sort out which joints are being used on which sides and having to deal with that extra level of logistics. Here are the planks. Once again, these are being made out of PVC, and those should slot in very easily into the joints. Here is the Gantt chart that we have created for the project, and you can see that at this point we are at the very beginning of April, and we are creating a new prototype with the redesigns right now. We are very close to finalizing our design, creating a final presentation, or we are in the process of creating our final presentation actually, and we are very excited for the final in-class presentation and also the Capstone Expo. Thank you very much. Let me know if you have any questions.